of, before Creo, when it was Pro E, got a Pro E4, it was called Mechanica before, called Simulate. It's the same thing. And it's got all this stuff here for thermal modeling, and we see here our usual sort of mechanical modeling. So I'm going to say displacement. I'm going to put this edge here and say that face isn't moving at all. And what I'm going to do then is I'm going to put a force going down on this face. So if I look at my directions, Y is the vertical direction. So in Y, I'm going to put a load here of, say, 2,000 newtons. Minus 2,000, so it goes down. Preview. That looks okay. So what I've got there is I've got held at this side, it's going down this side. So this is what I'm saying for your parts. You need to know geometry, you need to know restraints, how you're holding it, and you need to know loads. And you can see the kind of loads you can put on. You can put on forces, you can put on pressures, bearing pressure, obviously gravitational. Now, I need to tell it what material. So, this has got material library here. If we pick an aluminium, we can put it across here. Here's my aluminium. I can edit that aluminium and see what it is. Here's the aluminium. It's got a Young's modulus of 73 gigapascals. That sounds fine. It hasn't got yield strengths put in here. You can put them in if you want to. You can also put in failure criteria. And you see here we have von Mises and we have maximum shear stress. We also have to modify it more for brittle materials. But I'm not going to put any of those in. So, you see the label now on that. So it now knows it's material. And now I'm going to go analysis and studies. So you can see the kind of studies you can do. You can do a static, which is what I'm asking you to do. You can do a modal to calculate the natural frequencies of something, which could be useful perhaps for some people for projects. You can do buckling, fatigue, pre-stress, dynamic. Okay, it's not so. Creo isn't so good at dynamic sort of nonlinear problems. It's not good at all. So those of you that are doing projects for me, mostly are using ANSYS because ANSYS is a much more in-depth modeling package. It does, a stress analysis package. It does an awful lot more. But for this CA, I just want you to use this. So again, I'm going to give it a new analysis. I should probably give it a proper name. Now, I get into this in time, but I can do a single pass or a multiple pass. So I'm just going to do a single pass for a moment, and I'll explain what that means in time. And go OK. So it's ready to run now. I click the green flag, so that sets it running. And go yes. I click this sheet here, which shows me as it's running what's going on, and shows me any errors that are happening. It's run complete, like it was incredibly fast, because it's a very, very simple problem. Okay, so I can now go and have a look at the results of this using this button here. I should really, again, it's useful to give it names. If I look down here, what I'm looking at, the default comes up as von Mises stress. So if I go OK and show, now I'm looking at, so that's the von Mises stress on this part. Now I put the hole in just to create a bit of interest. So if I just go dynamic query, I can hover over it and I can see over here what the stress is. My units are in megapascals. The default up there is megapascals. So this is an aluminium part. I'm showing kind of a maximum stress here of about 14 megapascals. Is the part going to break?
No.
The purpose of all of this is to find out, is the part going to break? So is the part going to break?
No.
Why not? Sorry?
看这个颜色就知道了。
No, so the Young's modulus is 73 gigapascals, yes. But the Young's modulus and the yield are two separate things. They're not connected. Young's modulus is the slope of the stress strain curve. Yield is the point at which it becomes non-linear. So yield for aluminium is typically, we didn't set it in there, we could have. Typically, the yield for aluminium is about 250 megapascals. So it's not going to break at all. Say to 15 or something like that. So in this, that's what we use this for. We're also interested in deflection, because the deflection is a whole set of different equations. Stress is one thing and deflection is a separate thing. So as you've heard me saying before, if you think about something like a diving board, you want loads of deflection, and yet you don't want the thing to break, so you have to watch the stress. Sometimes you're interested in deflection. Mostly, if you're doing a beam in a roof, you want to make sure the deflection, usually the deflection is the criteria that's the problem, not the stress. Because you don't want a beam that's going to bend, because it's going to crack all your ceiling. So, in here we can go insert result window. So we're going to put a new window in. So if we go here, we can go displacement in millimeters and OK show. So this is our displacement of the beam. So we can see in millimeters that the red area is going 0.023. So it's very simple to use the Creo stuff. So in terms again of your project, if you're doing 3D modeling on your project, why not do a bit of Creo? Stress analysis using this. It's very, if you know your loads and your material and you've got your geometry, it's very quick and simple. Then if you want to impress people, yeah, you can, we'll put another one in, and this time we'll put an animation in. So what we're going to do is we'll do, instead of von Mises, we'll do maximum shear stress, and we'll go OK and show. And this time I'm doing an animation, so it's showing here. I can control the speed and so on of that animation. Slowly. So you can see the stress building up. You can do all sorts of other things in this. We delete some of these. So you can also do cutting planes, insert things like this. Insert capping, it's called capping surface. In the X, Y, and go OK. So now I can cut the thing to look inside the part and see what's going on in a plane inside the part. So this is what you have to do. You have to do calculations, as I've shown you, okay? And you have to do the modeling, and then you have to compare the two. That's it. That's the assignment, and that's all we're going to do from now.